Hello everyone, and welcome to another FRC Java tutorial by First Robotics Canada. In this video, we'll be introducing encoders, talking a bit about how they work, and some of the methods associated with encoders, as well as showing you a simple command with an encoder. As always, the commented code on GitHub, along with reference resources, will be linked in the description box below. Let's get started. First of all, what is an encoder? An encoder is a type of sensor which measures traveled distance. It counts what I'm going to call clicks, depending on how far the motor itself has rotated. So an encoder could record, say, 200 clicks per rotation of a wheel. Every encoder is different, so the number of clicks per rotations differs depending on the mechanism in the encoder. I'll be using an encoder class for this tutorial, but if you're using a Talon SRX, please read their documentation, because depending on the motor you get, you can use a built-in encoder in the Talon SRX API. The link to the Talon SRX, which has this documentation linked on its page, will be in the description box. Without further ado, let's get started. For this tutorial, I've decided to use encoders for the drivetrain, as that's a very common way to use them. I'll show you how to access them, as well as the methods you can use, and then we'll go through a very simple command that has you drive your robot forward to a certain distance. I'll be briefly discussing how to improve the use of an encoder at the end of the video, and some nuances. So if you're interested into looking how you might be able to do that, or what these nuances are, be sure to stick around. First off, let's look at the encoder objects I've initialized. As you can see, there are 4 parameters that need to be filled when creating these objects. The first 2 are the ports for the digital inputs. Again, I'm using RobotMap for this. The third parameter is a Boolean, which determines whether or not to invert the counting direction when the motor is moving. So whether the encoder clicks increase, false, or decrease, true, when the motor turns forward. The fourth value is the encoding type. There are a few encoding types, but we're going to use this one. If you're interested in learning exactly how encoders work electronically and what this encoding type means, I have linked that in the description. I have made a left and right encoder, as though there is a left encoder on one of the motors on the left side and one on the right. Let's take a brief glance at the constructor. Here is where you would set some of the settings or tuning options for encoders that we'll discuss in the enhancement portion of the video. But for now, I've just shown one such setting, and that is set reverse direction, which just flips the direction that the encoder is counting. You might be thinking, can't we do that when we instantiate the object? And that's true, but there may be some cases where you go backwards but want to count increasingly to make sure your calculations are a bit more straightforward. Now, let's get the measurement that the encoder receives. I've put this method here, which returns a double value from the getRaw method of the encoder. We might want to get the average between the left and the right encoders to improve our commands and make them easier, so I've done that here. Then, another useful thing that you might want to do is get a distance from your raw value. You can print your encoder values and measure, for example, how many meters there are per encoder value, and use that to convert your raw data into meters. I've done that here with a dummy value. It's important to note that your encoders will constantly be counting from the second that the robot is on. If you want to measure, say, 10 meters, then you could compare your current encoder value to the value it would be 10 meters later. However, it's usually 1,000 times easier to start fresh from 0. So there's a handy-dandy reset method, which I've associated with this method here, which resets both the left and right encoders. Keeping that in mind, let's move on to our command, which uses encoders. I've called it drive to distance command, because it drives your robot forward to a given distance using a given speed. As implied, I have distance and speed parameters in my constructor to be given when the command is called. In my initialize, I have the usual safety stop, but I've also reset my encoder so that I can facilitate things in the command. You'll also notice that I canceled drive here, just in case you use this command in teleop, so motors don't get conflicting values. Then, in execute, the robot drives forward only, as there is a 0 rotation argument until isFinish returns true. Here, isFinish will return true when the error between the encoder distance and the given distance is less than or equal to 0.1. Depending on what speed and what units you're using, you might want to fiddle with this error range, because if it's too small or your robot is going too fast, you might miss this range completely and your robot won't stop. Otherwise, it will stop, and the command will enter the end method where I stop the motors and start the drive command, which we have canceled. Now, You can hook this onto a when pressed button, but I've put this to start an autonomous, for the same reason as we previously had the timeout command, to drive over a line, with a sample distance of 5 and speed of 0.5. Remember, the distance units are whatever you set your conversion factor to. You might spot an issue already. What if I overshoot the error and my robot doesn't stop? The simple solution is to just use the timeout command if you're just trying for a simple autonomous mode, and that's what a lot of beginner teams use. It's consistent enough for such commands. But what if you want to do something more complicated? Here comes the part where I talk about improving using encoders, which you can look into if you're interested. First off, when setting up your encoders, there are a lot of things you can do to better tune your encoders. On this webpage, you can see these commands. These allow you to set tolerance levels for minimum rates your robot needs to be moving at to be considered stopped, and a method which allows you to set the number of samples to average to further tune your performance. It even has a built-in distance factor method, so you could then use getDistance directly. You could also use getCount, which is the actual number of clicks that the encoder records. In terms of fixing that overshooting issue, you could set your drivetrain to be a PID subsystem, create a PID method, or create your own PID tuner that changes your speed based on how close you are to the target using different tuning factors, which makes you less likely to overshoot. Documentation on PID tuning on screen steps will be in the description, and there are many resources online on how exactly to tune a mechanism with a PID loop. We have reached the end of yet another FRC Java tutorial. We're almost at the end. Our next and final video will be an introduction to ultrasonic sensors. Thanks for watching, and see you next time.